Yeah, I don't like that.
Okay, guys, so let's start. Let's start. So good afternoon, everybody. So, as I told you guys before, the purpose of this course is to learn how logic circuits. Okay, and logic circuits, as I told you, it can be combinational circuits. And this is what we have done in chapter 1, 2, and 3. Okay. And then we also have here sequential circuits. That's what I started to explain, should be in chapter 5 and 6. Okay. These are the two types of logical circuits. Okay. So for each one of them, you need to learn how can you design them. If you have a circuit, how can you analyze it? And that's what I did last time. So last time I explained, given a circuit, if you already have a circuit, how can you analyze this circuit? Analyze means how can you find the table, the state table, and also how can you find the state diagram? Just from the state diagram, you can know how the circuit works. You know what I'm saying? From the state diagram, you can know how it works. So here, as you see, from the state 0, okay, and the input is 0, output is 0, okay, and then here, if the input is 1, I'm going to move to state 1 and so on. Maybe this circuit just for education, it doesn't do anything. It doesn't do anything useful. Okay, just some random numbers, but I will show how can we design useful circuits. Okay, using sequential circuits. Okay, so that's what I explained last time. I give you here 5 examples. I give you 4 examples last time. Explain how they work, and you are gonna do a lab this week on this topic. Also, I told you we will in test number 2. I will give you a problem like the one here. So I will give you a circuit, and I will ask you to analyze it. Okay. The second part here in this chapter is how can you design a circuit. So 2 things. Given a circuit, how can you analyze it? This will be in test 2, okay? But in the final exam, I will ask you to design a circuit, okay? And that's what I will do here. But before I do it here, last time I did not explain, we have here 2 definitions. One definition here, we call it your circuit. We can call it milli circuit, or we can call it Moore circuit. So sequential circuit can be milli or more. Based on what? How I can know if it is milli or more? Very, very, very simple. Look here, guys. The idea is that if the output here, only look at the output. If the output is actually function in the states and also the input, this is what we call milli circuit. So if the output is actually calculated from the input and the state, that's what we call milli machine or milli model or milli circuit. Okay? For the second one, more circuit here, the output here only taken from the states, not from the input. I show here, for example, if you look at the circuit, this circuit here, this circuit is more. Why? Because the output here is just taken from the states, not the input. The input is not connected directly here. That's why we call it. This is more circuit. Okay? The input is not directly connected to the circuit, combinational circuit for the output. Okay, but if you see here in this circuit here, this circuit is actually milli, because if you look at the output in the combinational circuit that I'm using to generate the output, you can see here we connect here. B is connected here to this circuit. Okay, so the states are connected. Also, X is connected here. Okay, we have also this one here, which is coming from A. We have B, we have A, and we have X. As long as X, the input here, is connected to the combinational circuit to generate the output, it's milli. Okay, guys. So just a definition. If you have a circuit, you can tell if this circuit is more model or more machine or milli model. 2, okay? Again, I will repeat it because this will be a question in test 2. So in test 2, I will give you a circuit, I will ask you to analyze it. Also, I will ask if this circuit is milli and mole. Very easy. What I'm saying is that, look, only the output can tell. Look at the output. The circuit here we are using to generate the output, okay? If the input of this circuit only the states, then X or the whatever input you have here, you can have X, Y, Z, you can have multiple inputs, okay? But if you have whatever you have, as long as the input is not directly connected to the combination circuit you use to generate the output, this is more model. Merely model, the input is connected here, okay? Just the definition, but there is a little difference between them, okay? What is the little difference, small difference between them is, here, the output here is synchronized. What do you mean by synchronous? I mean, I'm gonna get, we're gonna obtain the correct output at specific times, the clock. Why? Because these flip-flops are gonna change their status at the clocks, okay? At specific times. That means I'm gonna get here, the input here, the new updated input will happen only at specific points. That's why the new value of y it can be taken at only specific points at specific times. Okay, either rising or falling edges. Okay, so that's why the output here is synchronized. However, the output here is non-synchronized. Why is non-synchronized? Because at any time when you change the input, for example, from 1 to 0, 0 to 1, at any time you will change the input, the output will change immediately. Even if it's a clock, even if there is 2 clocks, because I'm saying the output will change. However, this is not a big problem. Okay, if you want to make it synchronized, very simple. I can make here the output. I'm not going to allow the output to change unless at edges. So I can synchronize it. Okay, we agree here. Why is not synchronized? What it means? Because A is synchronized, B is synchronized, that's okay, because we have here B and we have A, but we have X. Okay, so A and B are synchronized. That means the new value for A and B is going to happen only at specific times. Okay, but X is not same. You can change X at any time. Okay, and by changing X, output is going to change at any time. You got what I'm saying? But still, it's not a big deal. If you want to make sure Y is synchronized, you have to make sure X is synchronized. Okay, how can you do that? Simply, at the X here, I can simply add a flip-flop here. Okay, and the output of the flip-flop is come here and X is here. You got what I'm saying? You see what I did? So what happened here is, even if you change X, it's not gonna be shown here except at specific times. You see what I did? So anyway, so this is just a small difference between them, but we can. If you want to make Y synchronize, you should not connect X directly here, but you can connect it through a flip-flop, so that even if X changes, for example, from 0 to 1, it's not gonna change the input system unless at specific times. Okay. Anyway, that's a small difference. But anyway, so again, what you need to do here, given a circuit, if I give you a circuit, you should tell if this circuit is more or nil, because I will ask in test 2 this question. Okay. And if you notice last time also, as I told you, sometimes the output, I did it in 2 different times. Always the input, we put the input here. So no, always the input is here. However, sometimes we put the output here, we put a slash this way, and then I put the output. Sometimes we put the output here. Okay, so sometimes the output we put it here with the state, or we put it here with the input. Okay, just to differentiate between milli and between mole, one of them, for example, here this one is mole because the output here is just depends on A and B. Okay, so that's why here, as you see here, we put the output here. So if the output only depends on a state, but we put it here. Okay, so this is the output here, slash we put it here. Okay, so usually we do that. In case of mole, okay, you have to, we usually put the output here. That means it means this output depends only on this state only. Okay, but if the output depends only also on the input, I'm gonna put it. What's the output here? I think we have another examples here. I think the first example I did that. Okay. Yeah. So if you see in the, because this is milli. Okay. So as you see here, this is input and this is output. Okay, guys. Just to differentiate between mole and milli. In mole, we're gonna put it here and actually makes sense because the output here depends on the states. So I put it with the states. But if the output depends also on X, so you have to put here with X. Anyway, that's not a big deal, but you need to know it. Any questions? Again, for test 2, you need to study these examples. Okay. The worst, this is my advice to you, the worst thing you can do, just you read the slides. Okay. And you think once you read the slides in exams, if I give you one of these problems, you can do it by yourself. Okay. You can do it. You will not be able to do it. Okay. So you have to solve. You have to solve the problem yourself, and then you have to compare it to the solutions you have in the slides. Okay. The next part here I'm going to teach is how I will jump here first and then I will come back. Therefore, I'm going to explain how can you design sequential circuit. Okay, not just given a sequential circuit, how can you analyze this? That's what I finished. What I will do right now is how can you analyze? We have specific steps here. The first steps from the problem description or from what you want to do. You have to draw the state diagram. This is the first step here. So from the problem, okay, or from what you want to design, based on what I for sure I will teach you more details. So the first thing you have to draw a state diagram, okay, and that can do whatever you want to do. Okay, I want to do something. I want to design a circuit that's doing something. The first step I have to do is I have to draw the state diagram. This is number one. Okay. So this state diagram has to do exactly what I want to do. Okay. This is usually the most difficult part. After that, everything here is just steps. So usually what you have here is just steps. You can straightforward steps, but usually the most difficult part is how can you make a state diagram that can actually does what exactly what you want to do. Okay, I can make an analogy here. For example, if you have a programming problem, okay, if you make a flow chart, you already solved the problem. The most difficult part is how to make a flow chart. Once you make the flow chart, anyone who knows C language, it will be easy to convert it from flow chart to flow chart is actually the same thing. Okay, I will teach you how can you do that, but this is usually the most difficult part. How can you, given based on what you want to do or given the problem description, how can you draw the state diagram? This number one. Once you have the state diagram, okay, once you draw the state diagram that's gonna solve your problem or it's gonna do whatever you want to do, you can hear. I'm going to talk about this step later. It's not that important steps, but I will talk about it later. Number two here, you need to assign binary values for the states. So when you design, for example, I can state 0, state 1, state 2, state 3, and then you make your design, whatever your design is. Okay, as I will explain. Next step, you have to assign values for these states. For example, here this should be state 0. This is and you need to know how many flip-flops you need. Okay, I give you very simple way last time. The number of flip-flops should equal to the number, or the number of states you have should equal to the power of n, where n is the number of flip-flops. Is that okay? That means if I have 4 states, that means I need two flip-flops. Oh, same thing if you have 3. If I need three states, also I need 2. 2 is gonna give you up to 4, right? So if you have 2 flip-flops, you can have 2 to the power of 2, you can have 4 states, okay? But if you need, for example, if I need 8, so if you have 8 states, that means I need 3 flip-flops. Same thing, if I need 7, also I need 3 flip-flops. Okay. Number three, you need to choose adjustment steps. As I told you guys, the most difficult part is just the first one. Once you have the diagram, everything after that systematic, just straightforward, easy. You will see right now. So the next step, you have to choose the type of flip-flops you will use, because I can design the circuit using G flip-flop. I can design it using T flip-flop. I can design it using J flip-flop. I can use any one of them. Okay, so you need to decide which one you have to use. Usually, we either the easier ones, or usually I will tell you in exams because it will be easy for me for grading. Otherwise, should have three solutions. Okay, for the flip-flop. So usually I will tell you, but you need to know. You need to know how to design it. It's the same way, but you will see right now. Usually, T flip-flop is easier, very easy. Usually, this T flip-flop in case of counters, if you want to make a counter, you will see right now. But in my opinion, I will show you how can you use all of them, but usually T flip-flop is just very easy. You will see right now. Okay? I will explain all of them. So the next step here, you need to decide what the type of the flip-flops you are going to use. Okay. After that, you need to find from the state. You already have here the state diagram. From the state diagram, you have to create the state table. Also, that's not difficult. Okay. From the state diagram, you need to make the state table. When I analyze the state, by the way, I did the opposite from state table to state diagram. Okay. Once you have the state table here, you need to find the inputs, as you will see right now. For example, if I use D flip-flop, I need to find what is the input. Okay. So for this state, in order to get this state, what should be the inputs of the flip-flop, and then after that, you need to design the combinational circuit of these inputs. Okay. Let me summarize, and then you will see that I will follow these steps in all the examples I have right now. Number one. Based on what you want to do, based on the problem description, okay, you need to draw the state diagram. This is the most difficult part. This is number one. Number two, from the state diagram, you can know how many flip-flops you need. You need to decide what type of flip-flops you need. Okay, you are going to use in your design. Okay, you can use either one of them for any circuit. Okay, so number three, you have from the state diagram, you have to make the state table. And then after that, you have what you have to do here. You have to find the input the input of the flip-flop. What should be the value of the input of the flip-flop? Okay. For example, if I use T flip-flop, you have to. If you use JK, you have to tell me what's the value of JK that can give me this. I will show you. So if this is the state, how I can get this as the negative state? What should be the value of T? What should the value of T of JK? Whatever you are going to use. Okay. And then after that, you can simplify these ones. Okay. Now you have combinational circuits for GA, combinational circuit for this one for GK. And that's it. You are done. You just draw it. Okay. I will follow these examples, these steps here. How can we do? Okay. So here in these examples, and this is, by the way, this is the project you will do. Okay. I will focus on two problems. The first problem here is how can you design a generator, sequence generator? Okay. The second one, how can you design a sequence detector? This is the two applications I will focus on, and this is what you will do the project as well. So sequence generator, okay, you can take from the English name, sequence generator. So I want to design a circuit to generate a sequence. Okay. So this sequence can be like a counter. For example, if I count here 0, and then after 1 clock, because this is going to change every 1 clock, it becomes number 1. After 1 clock, it becomes number 2, number 3, number 4, number 5, number 6, number 7, and then after 7, it's going to go to 0 again. Counter. Okay. So yes, this is a sequence. Okay. Or it can be as serial sequence, okay? So for example, it's gonna be, I wanna generate a sequence, something like that. 1100, and then you can repeat 1100, serial. Every clock, so here you can see. Anyway, I will give you more details. But anyway, so now in the examples you have here, and that's what you will do in the project. I emailed you, I posted the project, I made a video also for the project. So the project has two parts. One part should be very close to sequence generator. It's actually sequence generator. So before, and this is what you have to do next week, because the project will be done in 2 weeks. Okay, the remaining 2 weeks. So here, 1 week you are going to do the generator. 1 week you are going to do the detector. Okay, before you try it, you need first to understand the examples you have for the generator, and then you need to understand also the example for the detector when you do the detector. Okay, you can tell him. You can tell this is a detector. So what happens here, I can design a detector for the sequence, for example, 1100. And then I can connect the output of the generator to the end of it. So if the sequence here is 1100, it's detected by this circuit, the circuit will give you 1. So a circuit generates a sequence. A circuit is going to detect if the sequence is found or not. Okay. If you read the sequence something else, like 1010, so it's going to give you 0. Okay, but anyway, let's start one by one. But this is what we have here. So here I give you example, different way, or how can you generate different sequences. So it will be under sequence generator. Also, I'm going to explain how can you use sequence detector. Okay, any questions? Okay, let's start with sequence generator. And last semester, I give students only one example. That's why I added more examples. Okay. So I updated the slides. I sent you email about it. Okay, to add more examples. Okay, just nothing is new. Just I added more examples to understand it better. Okay. So let's start with the first one here. I wanna, but before I continue, so here. I'm gonna teach right now is how can you make a sequence generator. I want you to understand what I mean by sequence. What I mean by sequence here, for example, I have 3 flip-flops. Just an example. Okay. So here I can take the output of the state of the flip-flops here, the states themselves. Okay. So that means, and this is the example we have right now actually. Okay. So that means I can here every block. I'm going to get 3 bits. Okay, so here you have a circuit, which is here you have three bits. So this is 3 bit generator parallel. So every block I'm going to get 3 bits. Okay, for example here, as you see here, I'm going to start. I want to make a 3-bit counter. So as you see here, based on the description, it's easy. You can draw this one. Okay, that means look here, guys. So here I'm gonna start from 0, 0, 0. Okay, and then after the transition from here to here, every block will make transition. So after 1 block, I'm gonna get number 1. After 1 block, I'm gonna get number 2. After 1 block, I'm gonna get number 3, number 4, 5, 6, 7, and then I go to 0 again. Right? So if you look at the circuit here, you can see in the very beginning I have 0, 0, 0 because you have three outputs. Okay, this generator has 3 outputs. After 1 block, it becomes number 1. After 1 block, it becomes number 2. After 1 block, it becomes number 3 all the way until 1, 1, 1. And then, sorry, 3 ones. After 3 ones, you are gonna regenerate the sequence again. Okay, guys. So this is I will explain this one, but also I will explain we have another type of generator which is serial. So here you have only, and that's what you will do in the project. You have only 1 output here, and this output is only 1. Okay, and 1 output here. I want to see this sequence 1, 1, 1, 0, 0, and then you can repeat 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. You repeat it. Okay, that means it's going to be high for 1 clock. So the transition from here to here is going to be every 1 clock. So the output only 1 output, and then I will get it serial. But here I get it in parallel. Okay. But let's explain how can we design this counter here. Okay. But before any problem with the state diagram? Very easy. That's very easy state diagram. So here, state diagram, again, you should understand, we make a transition from one state to another every block. Okay? Any question? Is that difficult? So I need a circuit that will start from here and then we move here, here. And the output, my output here, I don't have here, there is no input. If there is no input, I can modify it to add input because this is a design. You will see right now, I can modify it to add input. And by the way, that's what we did last time, if you remember. So if I go last time, we had the last circuit I explained last time. Yeah, this circuit here, when I explained last time, we found this is a counter, this is counter, but this counter has one input. This input, if it is 0, it has input X, it's a counter, but it has input X. If X is equal to 0, so actually you build, but if X is equal to 1, you count. And you can tell here, look here, I have this animation is very interesting. So you will see here, I have 2 bits here. In the beginning, they are 0, 0, okay? And X is 1. So that means, look here, so here counted. In this period, you want to count. But here you have to both. So whatever value I have, the last value you are going to both. You understand what I'm saying? So let's see. So in the very beginning here, it was 0, 0. And then after one clock, when clock comes, becomes number 1. When clock comes, number 2. Because as long as it's 1, you are counting. As long as X is 1, you are going to move from 0 to 1. And then from 1 to 2, 2 to 3, 3 to 1, 0 again, and then you repeat. Count. At any time, if you are in this state, and X is 0, you are going to hold on here. Okay? You are going to pause it here. Okay? And that's exactly what I did. So now it is 1, 1, 1 here at this clock, every clock. So you can see here, whatever number you have here, you are going to keep it for 1 clock. 1 clock, 1 clock. Okay? Yeah, so here. And then here, because now X is 0, you are going to hold it. Okay? Because X is 0. Anyway. So, but now I want to start with something very simple that does not have any input or output. And you have to be careful here when I say, so when I say no input, okay, so we don't have any input here, okay? No output, you have to be careful here when I say no output, okay? For sure, there is no circuit doesn't have output, as I told you last time, okay? So I mean here, we don't have a combinational circuit to generate an output. That's what I need. But actually, the output will be taken from the states. So the output of the circuit will be from the states themselves or the output of the circuit. I don't need to make a combination circuit to get an output. That's what I mean. Okay? So anyway, any problem about this one here? I think that's very easy because it's a most difficult part. After that, just the text. Any problem for this one here? I start with something simple. It doesn't have input or output, but later you will see how can I add. You can add. I will complicate it. Okay? By the way, this is very important thing. By the way, I can design this counter to this counter is counting up. I can simply design the same thing to count down. You got what I'm saying? Yes. So for example, here it's gonna be this way. Okay, 0, 0, and then 1, 1, and then here number 7, then number 6. So all what you have to do just you can design it to count down. Is that okay? Not only that, I can design it to give me any sequence. It's not only counting any sequence. So the way I did it here, after 0, 0, 0, I want to get number 1 because I'm counting. After 0 comes 1. After 1 comes 2 because I'm counting. But easily you can design it to have any sequence. For example, for some reason, I need this sequence. After 0, I want to get number 4. So I'm going to put 1, 0, 1 or 5. Okay? And then after 5, I want to get, for example, number 1. You understand what I'm saying? So easily you can change this once, and then you can follow what we are going to do. The circuit will work. You understand what I'm saying? So here, yes, I give you a counting up, but easily you can change it to counting down. You can easily change it to any sequence, not even counting, any sequence. Okay? But here is the output we have in the circuit here. We have 3 outputs. Okay? Every block we get 3 bits, not 3 outputs, 3 bits. Okay? I will teach you now because that's what you do in the project. Only one output, 7. But anyway, Any questions? Any question about the state diagram? Because this is the most difficult part, by the way. After that, everything is just straightforward. Okay. So okay, now I'm done with this one. I need a circuit that generates states this way. The next thing you have to decide how many flip-flops you need. In this case, because I have 80 states, so I need 3 flip-flops. Is that right? So the 2 to the power 3 is 8. So now, yeah, I decided how many flip-flops I can have. Next step, we need to decide which type of flip-flops you want to use. Okay, so in these examples, I will focus on G flip-flop, but also I will show how can you do other flip-flops like G, like G key flip-flops. They are almost the same. There is a small difference, but I will show you them. Okay, so here, assuming here I decided to use T flip-flop. Is that okay? Next one here. Okay, from the state, next is just steps. Every time I will follow the steps. Next step here, given the state diagram, you need to make the state table here. The table should stop here. Okay, you need to add this part, but anyway, so you need to make the table here. Okay? So in order to make this table, number one, as I explained last time, you need to put the states here, which E0, E1, E2, which these are the outputs of the flip-flops. You have to put all possible cases here. Make sense? Okay, and then you have to talk about next state. In order to calculate the next state, I need to use this one here. Okay, let's see how can you make it. Look here, guys. If the current state 0, 0, 0, what is the next state? Yeah, look here. If it is 0, 0, next state is 0, 0, 1. I'm gonna write it here. If you have a different number here, okay, you have to put it here. You're designing. So here, I want to make a circuit. If the current state is 0, 0, next state should be 0, 0, 1. Number 1. Okay. So again, from the table here, it can be, again, as I told you, it can be 1, 1, whatever you have here. It depends on what you are designing. Counting down, counting up. If you are designing some random sequence, whatever you are designing. So you have to see here, based on what you have in the state diagram. If the current state is 0, 0, what is the next one? Okay, this diagram is telling me from 0, 0 it has to be 0, 0, 1. Okay, so I finish this one. Same thing for the next one. If the current state is number 1, which is this one, what is the next one? It has to be this one. So I'm gonna put it here. Makes sense? So I have, again, let me say it again. Number 1, you have to put the states here. We don't have inputs. If you have input, I would put it here, but we don't. Okay. Also, same thing. If I have output, I would put it here, but we don't. So that's why here we have all these states and this state. This is a current or present state, and this is the next state. Okay, based on this diagram, you can see if the input is 0, 0, the next state has to be 1. Okay. If the input is 1, the next state is 2. If the input is 2, because this is count, okay, count up. Okay. You can design to count down, or it can be any random sequence. It's gonna work any random sequence. Okay. Whatever you write here, you can write here whatever you need next. So if the current state 0, 0, what's the next state you need? Whatever you put here, that's what you will get. I'm designing. So whatever you write here, that's what you will. Same thing here. If I have number 2, then I will get number 3. If I have 3, I get 4. If I have 4, so the next one 5. If I get 5, next one is 6. If I have 6, next one 7. If I have 7, next one is 0. Make sense? Any question here? So again, for this one, you have to put all possible cases. To get from here to here, you have to use the table. Is it easy? Any questions? Okay. Okay. Next, again, guys, please listen to me. Don't just read the slides. You need to solve it by yourself. And you can try other things. Here, I told you, for example, here I did count up. You can try count it down, and you can use the simulator you have to simulate it to make sure it's working. Okay, the digital simulator. Anyway, so now I finish this one and finish this one. What is the next step? And now I finish the step table. So the next step is, okay, I need to find what is the input of the flip-flop that, if this is the current state, it's gonna make this state next time. what should be the input? What should be the input of the flip-flops that can achieve what I want to do here? If this is a current state, okay, what should be the input? So what I'm saying here, guys. So what I'm saying, if this is a current state, the input of the flip-flop should be 0, 0, 1, so that next time I will get 0, 0, 1. Okay? Let's see another example. Here, if the input is 1, 0, 0, okay, in order to get next time 1, 0, 1, so this should be the input of the flip-flops. Okay, this if the input of the flip-flop this one, I can make this transition from here to. But how can you calculate it? Very easy. You will see right now how I can calculate it. So now, because I have 3 flip-flops and every flip-flop has only one input, which is T. So I have T A2, I have T A1, I have T A0. Because every flip-flop has only one T. Okay, you know how T flip-flop works, right? The way T flip-flop works is if, okay, look here, guys. If the flip-flop is storing 0, and next time, here, look here, guys. So now, for example, here I will start from here. Look at this one here. This flip-flop number 2 is storing 0. Next time, I want it also to store 0. What should I put here in the input so that if it's storing 0, next time also I get 0? What should I put here in the input? 0 or 1? 0. Why? Because we know how T flip-flop works. In T flip-flop, when T is equal 0, no change. So when T is equal 1, toggle. Yes, that's why I have to put 0 here. I have to put 0 here in this one, so that if the current is 0, next time I will also get 0. Okay. Let's see another one. Use the different color. Here, same thing. I have 0. Also, next time I want to get 0, so I have to put here 0. Okay. Next one. Also, I have 0 here. Next time I will get 0. Okay, so I have to put here 0. Let's see next one. Look here, guys. Now here I have 0, but next time I need to get 1. So in this case, TA has to be 1. I have to design a combinational circuit so that in this case it has to put 1. This is the main idea. That's exactly what I will do. Okay. So here, so again, all what you have to do, guys, I'm gonna compare the present state for each flip-flop to the next state. If I find it is the same, I'm gonna put 0. Okay, in order to achieve this transition from here to here. If I find it's toggle, I'm gonna put 1. Okay, so you have to finish all the way here. So for example, here we have 1, and this one is 0. So I have to put here 1. Here it is this one is the same 1, 1, so it has to be 0. Okay. Now it is 1, 1, it has to be 0, 1, 1, it has to be 0. Is that okay? Make sense? Okay. Now I'm done with the first flip-flop. You have to repeat again for each flip-flop. Same thing again. Okay. So here again, here I have 0. Here, next time I want to get 0, so I have to make sure the combinational circuit has to make sure there is a 0 here. If you have here 0 and then 1, so it has to make sure it should be 1 here. 1 and 1, so it should be 0. 1 here, this one was 1, and then next time it has to be 0, so it has to toggle. Okay, so here 0, 0. Okay, so again, I will compare for each flip-flop. I'm gonna compare the current state. Okay, the current bit for the next bit. If they are, in case of C flip-flop, if they are equal, so I have to make sure the combination still has to put 0 here. Okay, because 0 is gonna make no change. If it is toggled, okay, so I have to make sure I put 1 in. Any question? Is that difficult? So again, so what I did here, guys, number 1, I started with this one here. I put all possible cases, and then with the help or using the state diagram, I was able to fill up this part, and then I was able to derive this part from these 2 inputs here. I can derive this part here. Is that okay? Any questions? You are almost done. We are almost done. So now, here, I need to design a combinational circuit so that if this is the input, there should be this is the output. So I need to design a combinational circuit. The output of this combinational circuit has to be connected to GA2, and this is the input. It's going to come from here. Another combinational circuit, this is also the input here, but the output here will be GE1. It's another combinational circuit. This is the input, and the output here should be GE0. These ones. So I need to find the combinational circuit that given this input is going to generate this output here. Okay, sorry, this column here and this column this way, and I need to connect them to the three flip-flops. Make sense? So for sure, I also, similar to what we did before, we need to do simplification. So that's why if I go to next slide here, you can see here. First, I need to do simplification. These are the three inputs you have. You remember when you use the key maps, still I need to use key maps. You remember when I explained key maps, I told you the first one here, whatever the name is, has to be here. We call it WX, whatever the name has to be here. The second one here, whatever the name is, has to be here. The third name is the third one here has to be. Okay. So again, all what I did here, guys, if you look here, if you look at GA2 here, for example, this is 0, 1, 2, 4, 4 and 7. So here at 4, sorry, 0, 1, 2, 3, this is 3 and 7. So I'm going to put 1 at 3, 1 at 7. Make sense? Key maps. And then I will simplify it. So this is the result. So GE2, the input of flip-flop number 2 should be A1 and A3. Okay, so that's why if you see here, when I design it, this is flip-flop number 2. Okay, you can see here the input of this one has to be A1 and A0. And okay, let's try E1. See what's happening for E1. Same thing here. I will try. This is the input I have, and this is the output of the combinational circuit. So I will do it here. You can see this is 0. This is number 1, 2, 3, and 4, 5, and 7. So I have to put here 1 at 1, and main term 1, 3, 5, and 7. Okay. So now I can take this 4 only as one group, and then the output here is E input. Okay. So that's why here this one here is connected to. Okay. Let's design the third one. The third one here. It's very interesting. You can find here it's just one, all of them. So all of this function is giving. You don't even need to draw this one, because once you find the function, so always 1, regardless what is the input, so actually f here, f is equal to 1. Because it's all give you 1. Okay, so that's exactly what I did here. So here you can see here I have to put 1. Okay, I'm not. You are done. Okay, so what I did right now, I can repeat for every example. I will do exactly the same thing. That's why you can see, guys. The most difficult part is how can you do this one. Okay. For sure, this example is not difficult, but in general, because everything after that will be systematic, just steps. You need to follow steps. Okay. And this is how the circuit should look like. This is the clock, so you can see we change. So here in the very beginning we have 0, 0, 0. Okay, and then after one clock, after this clock here we have number 1, and then after that we have number 2. And then we have number 3. This is the timing diagram. And then after that, we have 0, 0, 1, which is number 4. And then we have here 1, 0, 1, which is number 5. And then number 6. And then number 7. And then after 7, I will go 0 again. You repeat again, go to 0 again. Because this is how counter works. You count from 0 to 7. After 7, you count again from 0 to 7. 0 to 7, 0 to 7. That's how it works. Okay. Any questions? Okay. I will tell you something here about this design. Look here, guys. If I don't design the circuit this way, if I don't design, I wanna make a circuit that can do this diagram here. Okay. From this diagram, you can have several observations that can help you to design the circuit even without making making state diagram, state table without all of that. But this only in case of counters or in some like counters because it's easy. Okay, so let's see what observation you have here. Okay, let's see the observation. Number one, if you look at E0, it's always for every clock it's toggle, all the time toggles. See what is the relation between the clock and E0. What you can see here. I see E0 for every clock has to toggle. Every clock has to toggle. Okay? So what should be the input of the different clock that can toggle every clock? Has to be one all the time. You can figure it out from here. So that's why here, that's why I need something here. That's why I'm gonna fix here one so that every clock is gonna toggle. Because this is the observation I have here. Okay. Let's look at the second one here, E1. You can notice E1 should toggle only when E0 is equal to 1. So here, look here, E0 is equal to 0, so it should not toggle. Okay? So here, when it is 1, when this one is equal to 1, it's gonna toggle. Also, same thing here, when this one is 1, it's gonna toggle. So you can see E1 is gonna toggle all the time only when E0 equal to 1. When E0 equals 0, no change. You got what I'm saying? That is why you can see here, T should equal to E0. So that when E0 equal to 0, no change. When 0 equal to 1, it's gonna toggle, because this is what I see here. That's what I want to do in this sequence. Okay. Let's do the next one. You can for E3, there is a certain pattern right now. Okay, so here I design 3-bit. But based on the pattern I will have right now, you can make it 6 bits, 8 bit, because I have a pattern. You will see what is the pattern now. So now you can see E3 has to toggle when both. Every time E0 is 1 and E1 is 1, this one has to toggle. You got what I'm saying? So you can have this observation. That's why I put AND here, so that I'm gonna have 1 here to toggle only when the 2 inputs here are ones. Look at what I'm saying. If I wanna make 4, if I wanna make it E4, you will notice toggle is gonna happen when the previous 3 are ones. This is a pattern. I didn't invent it. Okay, if you want to make numbers, you can see we have a certain pattern there. That's why if I want to extend this circuit to add 1 more, okay, you may not have this observation in other circuits, but just here I have this observation. That doesn't mean for everything I should have an observation like this one, and I don't need a state diagram all the time. No, it's only here. Okay. So if I add 1 more here, okay, so that means I'm gonna need AND, okay, without even making state diagram or whatever, because I have a certain observation here, and then here I will connect A node, I will connect A1, A2, so that this one is going to toggle when all of them are ones. Okay, when at least one of them is 0, there should be 0 and no change. Anyway, same thing, you can extend the more if you want. Any questions? Okay, let's have more examples I made here. For example, I want to make 2-bit counter, okay, but now I want to add 1 bit for pause and resume. Okay, by the way, this is the example we have before, but I'm going to do it in the opposite way. So here, the example we had here, this example number 4 here, I give you the circuit, in this example here, I give you the circuit, and I ask you to analyze it. Now I will do the opposite. Okay, now I want to design this circuit. That, you know what I'm saying? So I should get this one at the end. So now I want to design this circuit. Okay, not analyze it, just I want to design. Okay, again, the most difficult part is how to make the state diagram. The state diagram has to be this way, guys. Now I have input here. Look here. If the input is 1, I should count. So that means here I'm gonna make it for 2 bits. Okay. So as you see here, if I'm 0, so after 0 should be 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Counting. You can see here. So as long as x is 1, it's gonna count. But if x is 0 at any time, you have to hold on. You have to pause. You have to pause at this stage. So if the count is 0, okay, and then x is 0, so I'm gonna pause at 0. So every clock comes 0, 0, 0, 0, because I'm pausing. Okay. Once it is 1, you are gonna resume. Same thing here. If x is 0, I have to wait here. If x is 1, I have to wait here. If x is 0, I have to wait here. X is 1, I have to move to the next one. So you can see very simple. For every state, if x is 1, I will go to the next state. But if x is 0, I'm going to stay in this state. Okay? This is the most difficult part. Once you finish this one, everything after that is systematic. So again, similar to what I have just said. Okay, now you have what inputs you have here. I have two states, as you see here. I have two states and I have x as well. Two states and x. I'm gonna put all possible cases here, all possible cases. Is that okay? And then to move from here to here, I need the help of the diagram to move from here to here. Look here, guys. If I'm in state 0 and x is 0, what should be the next state? As you see here. Okay, so the next state has to be 0. Make sense? Let's see the next one. But if I'm in state 0 and x is 1, so the next one has to be 0, 1. Okay? If I'm in state 0, 1 and x is 0, if I'm in state in 0, 1, x is 0, okay, which is this one here. So for every arrow, you're gonna have a row here. That's why the number of arrows here should equal to the number of rows here. In exams, in anything, if you find the number of arrows does not equal the number of rows, so something is wrong. Because for every arrow you have one row here. Okay. So here, if I'm in 0, 1, x is 0, I'm gonna stay. You have to stay in 0, 1. Guys, I'm designing it. I'm telling the circuit. That's what I'm doing. I'm telling the circuit. If you are in state 0, 1 and x is 0, you have to stay at 0, 1. Design. I'm designing it. You got to say it's my choice. Anyway, so also here you can see if it is 0, 1, but x is 1, please next time you have to move to 1, 1, 0, and so on. Okay. So again, here this is the step. Number 1, you have to put what the state and input you have to put in here, and then you have to write all possible cases here. This is number 1. Number 2, to calculate this part here, you actually need the state diagram. Okay. Now, I need 2 flip-flops. I decided to use T flip-flop. Okay. Here in this example, I focus on T flip-flop, but it doesn't mean always we can use T flip-flop. Okay. I think G is easier. I think in case of G flip-flop, GA1 is equal to A1. So you don't even need to count. You don't even need to calculate these values. Okay? Because if I want to get 0, D has to be 0. Next time if I want to get 0, D has to be 0. So actually, this one here has to be the input for G flip-flop. So usually D flip-flop is easier, but in case of counters, we like to use T flip-flop. Anyway, regardless, okay, so here I want to do it using T flip-flop. I will teach you how can do using other flip-flops. Okay? So anyway, so you can see here, guys, similar to what I explained here, 0, and then next time I want to hit 0. So that means no change. So I have to make sure the input here is 0. Same thing here, 0, 0. You have to make sure it is 0. 0, 0. I have to make it 0, no change. Now it is 0, but next time I want to make it 1. So the combination circuit has to make sure the input in this state has to be 1. So if the input is 1 and the flip-flop is storing 0, next time I will take 1. Okay. Again, similar to what I explained, you have to fill up this part here, you have to fill up this part. Any questions? Same thing, similar to what I did. You need to get, this is like a combination. Now you have a combination. This is like F, and this is like WXY. We used before WXY and F. So now you need to get F as a function of this inputs here. So that's why you need to use emaps. So here when I use the emaps, I found TA1 equal to XA0, which is this one here, this column here. This column also I have to do it. I found it is TA0 is equal to X. Okay, so if you see this circuit, this circuit will be similar to the circuit we had before. Hopefully, I don't know. Let's see. Let's go back. Regardless of that. Yeah, so here we have one of them have X, okay, which is actually B. One of them has AND for X and B. Okay, I think that's exactly the same thing like this. Anyway, Yeah, so one of them has X. I just flipped it. So here, A0 is actually B in the other one, and this one is A. Okay, I just flipped it. But it's the same thing. Okay, guys, any questions? Let's have another example. It's the same examples here, but I want to produce a sequence. Yeah, this time I'm gonna teach how can you produce a sequence is sequential, serial. Okay, so here what I will do here in this example is I have a combination circuit this way, and I want to, and that's what you need. That is exactly the same thing, but that's what you will need in the project. Okay, so here this is a frequency generator, but I need output here. So I'm not gonna get, for example, if you have 3 flip-flops, I'm not gonna get the output of the 3 flip-flops as I did before. Okay. So here I'm gonna have a certain output here to generate a certain sequence, a serial sequence, something like 1100 or 1010, whatever is the sequence you want to generate. Okay. Okay, guys. This is the difference again. This is the difference between what I have explained right now. We're gonna get the output from the flip-flops. Okay. That's why every clock, and here I'm gonna get two bits. In the previous example, every clock I got 3 bits. But this time, every time I get only 1 bit. Okay. So I need to design a combination circuit that's gonna generate Y out of X and the states, or only states. Okay, depends on the design. Okay, so let's see how now again, nothing is new, guys. Similar to what I explained, you have to start from here, and then once you have this is a multiple part. Once you have the state diagram, everything after that just follow steps. It's easy. So let's start with this one here, guys. Here, I want to generate this sequence, guys. Here, 0. Again, this example is very important because this example is exactly what you will do in the first part of the project. All what I did, I just changed it. I think, as far as I remember, I just changed the sequence. I think the sequence will be 1100. That's it, but everything else is the same. So this example is very close to what you are going to do in the first part of the project. So now I want to generate this sequence series. So every clock, you have only one output here. Okay. So in the first clock, I'm gonna 0. 0 is gonna stay for 1 clock, and then 1, and then 1, and then 0, and then it's gonna repeat. 0 1 1 0 0 1 1 0 0 1 0 1 1 0, and so on. It's gonna repeat. Okay, but I want to generate a sequence this way. Let's see how can we do it. Look here, guys. Now, number 1, how many states do you need? This is the first question. How many states? In this case, actually here, this is 1 state. So every bit here in the sequence, 1 state. That means I need 4 states. Here, the number of states equal to number of bits in the sequence. That means if I want to get that sequence that's 8 bits, I need 8 flip-flops. 3 bits, 3 flip-flops, and so on. Okay. So here, that's what I need here. Not the number of states, because in the first state I want to generate 0. In state number 2, or for example, if you say state 0, state 1, state 2, state 3. So number of states, not the number of flip-flops. You know already the relation between number of flip-flops and number of states. So now I need 4 states. Okay, so as you see here, guys, it's very easy. You look here. Okay, so now if I'm in state 0, I have to make sure the output is 0. And then when the clock comes, I have to move to state 1. And in this state, I have to make sure the output is 1. Okay. Here, if I'm in state 1, so next clock, I'm going to move to state 2, and the output is 1. If I'm in state 2, I'm going to go to state 3, output is 0. If I'm in state 3, then next clock, I will come here, and the output is 0. Makes sense? So here, I'm going to move from one state to another. In every state, I'm going to produce 1 output. And this output should be 0, 1, 1. Okay? That means this example is very close to the project. So in the project, if it is, I shouldn't say it, but if you want to generate 1, 1, 0, 0, so you have to use exactly the same thing I did here, but you have to put here 1, 1, 0, 0. That's it, you finished. You got what I'm saying? Yeah, so here I'm going to generate. So if I'm in state 0, I want to get 1, 1, 0, 0, or any other sequence. So for example, if I want to generate 1 0 1 0. So I have to make sure here. Design, you're designing. I'm asking the circuit, I need 1 here, and then I need 0 here. I need 1 here, I need 0 here. You will reduce it this way. Okay? So that's why it's our first part of the approach should be simple modification to this example. Okay. Any question here? Because after that, everything is just systematic. Okay. Okay. Now you need to ask yourself how many flip-flops. I think in the project here, I'm going to design it using T flip-flop. I think in the project, I asked you to do it using G flip-flop. There's a small difference. I will tell you about it. Even G is easier. Anyway, so number two, you need to ask yourself how many flip-flops you need, because I have 4 states, so I need 2 flip-flops. Is that okay? So I need 2 flip-flops, E0, E1. Okay. So here, this is the inputs. Always here, guys, you have to put the states and inputs. Okay, states and inputs. So here we have only 2 states. We don't have any inputs. Okay. Here, you have to put the new states. So this is like the present state. This is the next state, and also have to put output if you have. Always we do that. Okay. So here the present state and input. Here the present state and output if you have. Okay. Okay. So here, once you have this one here, you just put all possible cases. Let me use a different color. Okay. So here I'm gonna put all possible cases 0 0 1 0. Okay. Again, same as I said before, to move from here to here, I need the help. I need the help of the state diagram. Okay, guys. So now, if the current state is 0 0, please make the next state is number 1. So from here, we're making this transition from here to here, number 1. And the current output is actually 1. We have to make sure the output is 1. So if this is the current state 0 0, I have to make sure the output is 1. Also, so the output here, this may be confusing to you because this is applying G, this is applying G dot 1, but for the output, we only design applying G. So this may be a little bit confusing to you, okay? So you have to use this one. So if I am in state 0, I have to make sure the output is 1, and I have to make sure the next state is actually number 1. Okay? This is one move. So here, for example, if I'm number 1, I have to make sure next time I will go to state 2, yeah, which is actually from here to here. I need to make sure the current Y is 1. Okay. If same thing here, if the input here is 1 1, which is actually this part here. Okay. If this is the state 1 1, I have to make sure Y is 0. Okay. I have to make sure that when the clock comes, the next one is 0 0. Okay. That's easy. After that, because look here, guys, because I want to use T flip-flop. So now I have to find what should be the input of the flip-flop that can achieve this transition from here to here. Okay? What should be the input of the flip-flop so that when I have 0 0, the combination circuit is gonna make sure this input is gonna move from 0 0 to 0 1. Okay, what should be the input here? Okay? So the input here, as you see here, guys, is actually, if you look here, 0, and then I want to stay 0. So it has to be 0. 0, and then I have to toggle to 1. So I have to make sure this one is 1. This combination circuit has to make sure of that. Okay? In this case, it has to go to 1 here to make toggle. Now 1 should be stay 1. So I have no change. 1 has to go to 0, toggle. Makes sense? I don't need to keep repeating, but this is after that you already have this one and this one. Okay. Now you need to simplify. Now, look here, guys. I need to design three functions. One for this one for this one, and one for Y as well. One for Y as well. Okay. Here, because we have only 2 inputs, keep maps. I don't need maps. I can just use simple algebra manipulation, and that's what I did because it's just 2 inputs. So let's look at them here. This one is very easy. 1 1 1 1 1. So all the time it has to be 1. Makes sense? Okay. Now let's look at the second one here. TE1 here. Yeah, so here you have 1 here and we have 1 here. Oh, don't be confused. Here, this one has to be function in the current state, not this one. So don't, here I'm designing everything related to this one's here. Not this one's here, okay? So here, if it is 1, so 1 here should be A1 prime, you remember A1 prime Eno. Okay, this one here, this one should be A1 Eno, as you see. And then you very simple simplification, I found this one should be Eno. Okay. Same thing for Y. If you see Y here, okay. So if you see Y here, I have two ones here, one in this case and one in this case. Okay. So for this one, you have here A1 prime, A0 prime. For this one here, you have A1, A0 prime. And then very simple simplification, I find this one A1 prime. So Y is equal to A1 prime. Okay. GA0 is equal to 1. So if I come here, GA0 is 1. Okay. GA1 is equal to E0. That's what I did here, E0. Y is actually E1 prime. So I can take it, I can put inverter this way, or actually I can take it from here. I forgot when I did it, okay? So you can actually take E1 and invert it, or because already every flip-flop gives you the value and the inversion, so I can just take it from. Any questions? Good. So in the project, I will ask you to use D flip-flop, which is easier than this one. You know why? Why it's easier? Because in case of D flip-flop, you don't need to calculate, or here, if you want to get GE1 and GE0. Actually, DE1 is actually equal to A1, so you need to copy it here. And this one, you have to copy it here. So that's it, because it's much easier, okay? Because in case if D is equal to 0, Q is equal to 0. If Q equal to 1, Q is equal to 1. That means if I want to get 0, okay, so I have to make sure D is 0. If I want to get 1, I have to make sure D is 1. If I want to get 1, I have to make sure D is 0. You got what I'm saying? So again, you don't need, sometimes actually in some of the examples I didn't even write this one, and I just work it on these two. You got what I'm saying? So what I'm saying, in case of D flip-flop, this should be the input. If I want to get 0, I have to shift the input to 0. So I don't need even to add two more columns, I can just use this. Okay. And then same thing, you can do simplification similar to what I did here. Okay. The last example I have here is actually, okay, I want to show you here for some reason, I want to modify this circuit. I just want to give you one example. If you have, here in this circuit, you have output, but you don't have inputs. You have always we have states. We don't talk about it. So always we have states. Sometimes you have inputs on top of the state. Sometimes you have output. Okay. So here you have states and you have output. You don't have input. So now I want to modify this circuit. I want to modify this circuit to add one input. This input can resume counting or not counting. Resume sequence or both sequence. You got what I'm saying? So now what I mean is I want to modify this circuit to add one input so that if this input is equal to 1, the sequence should be 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. It's working. However, if x is 0, you are gonna put both. When you put, for example, if I'm gonna put at the 1 here, if I put at the 1, so you're gonna have 1, 1, 1, 1, 1, 1, 1. So you are not gonna complete the sequence. Okay. For example, I wanna just so here I'm gonna modify this example to add also in addition to output, I can also add input. Okay? And this is actually that's what you would do through the project, because in the project I told you you have here you need to generate one of two sequences, either 1100 or 1010. But also we have here input. This input will be selector. If the selector is 0, you have to generate this sequence. If the selector is 1, you have to generate this sequence. You got what I'm saying? That's why the next example also is important. Okay. So you need at least these two examples. You need to understand them very well before you try the project. Okay. So here in the project you have one input, and I want to generate two sequences based on the selector here. If I select the sequence, if I put it 0, I want to generate a certain sequence. I don't remember for sure which one. So you need to go to the project description. If the input is 1, I will generate another one. But I have two sequences based on the input I have, I generate. So here, again, I need to modify this one so that I need to see how can you modify. Okay? So I will do something very close, but this time it's going to be like both. So if you see here, guys, this circle, I want to modify this circle to add a both. So all what I did here, guys, as you see here, when I added here, this is a new one. This was not, everything is the same, but this was not here. I added it. So then I'm saying, if I'm in state 0, you have to output 0. That's okay. And if x is 1, you have to move to here. X is 1, you have to move to here, output 1, 1, and then you have to output 0, okay? And then 0 again, okay? So you can see here, this one is similar, 0, 0, 1, 1, 0. So it's similar to this one. However, I added here, if x is 0, you need to wait here. If x is 0, you have to wait here. If x is 0, you have to wait here. If x is 0, you have to wait here. You see how I made it? So again, if I'm in this state, x is 0, you have to wait here. If x is 1, I have to move here. If x is 0, I have to wait here. If x is 1, you have to move here. X is 0, you have to wait here. If x is 1, you have to move here, and so on. So that at any time, if x is 0, you are gonna stay in this state. Okay. So number one, how this will change the way you make the table here. Yes, it will change it because now you here you have to put the state. I have two states. Okay. Why you have to state? I have two flip-flops. Why you have two flip-flops? Simply because I have 4 steps here. You have 4 steps. Okay? Also, I need to add the input x's here. So this time I'm gonna have 8 cases. Last time I didn't have x, that's why I have only 4 cases. Okay? So I need to add x here as well. Okay? And then I have to put all possible cases here. So here you have to put the states you have, the flip-flops you have 2 flip-flops and you have x. Okay, and then you have to write all possible cases. Okay, that's easy. Now I need to know, similar to what I did before, what is the new value for EZ1? This is a negative state and 1. Okay, this one. And in order to move from here to here, I need the help of the state diagram. Let's do it. For example, here, guys. If I am 0, 0, okay, and x is 0, so next time it has also to be 0, 0. And y is 0 here, as you see. Makes sense? But if it is 1, so next time you have to go to state 0, 1. I think I made a mistake here. I'm sorry, I will correct it. The mistake I made, here y has to be 0. I will correct it, okay? Here y has to be 0 because I'm still in state 0, 0. Okay? So I will correct it. Okay? Let's see another one. Let's see. So for example, here, if I'm in 0, 1 here, okay, and it is 0, so I have to stay in 0, 1, and you have to produce 1. Okay, so this one is okay. This one is wrong, so it has to be 0. Okay. So same thing here, if I'm in 0, 1, but it is 1, so I have to move to the next stage, which is 1, 0. But for y, this is the part I told you was going to confuse you. So this is actually t of 1, but this is at t, and this is at time t. Okay. Okay, so this one is okay. Now let's look if I'm at 1, 0 here. Okay. If x is 0, I have to stay 1, 0, and the output is 1. So this one is okay. This is wrong. So this one, okay, I will correct it, but I will do it if I missed it. Okay. So next one here, if it is 1, 0, and then here it is 1, so I'm going to move here. But for here for y, I have to take y, not for this one, no, for this one. Okay. So this is a mistake I made. So this is y applying g, not t plus 1. Okay. So anyway, I will correct it now. Also, I will correct it again and put it in. Okay. Anyway, so now if it is 1, 1, if you have 1, 1, and it is 0, so you have to stay 1, 1. And the output is always, as long as 1, 1, the output has to be 0, 0. Okay. So, but here if it is 1, 1, you have to go to 0, 0. Okay, guys. So again, similar to what we did before, I need to find GE1 and GE0. So if this one is 0, and then you want to, this one here is 0, and then you want to stay 0. So I have to make sure, just give me 1 minute, 0, 0, I have to make sure this one is 0. If this is 0 and then it has to stay 0, you have to make it 0. That's easy, right? So once you have GE1 and GE2, so you can actually summarize, you can actually minimize them this way. Okay, just give me 1 minute. Okay. But here, so I need to change y. So here, in one. Do this, the last thing I want to see here, guys, to design. I will modify this one because I made a mistake here. This one should be 0, this one, and you should be avoid this mistake. So whatever y here has to be corresponding to this state, not the next one. This is a mistake I made. You shouldn't make it. Okay. So last thing I want to show here, guys, I can design this circuit to give me the output, okay, using mode model or Mealy model. Okay. So if you want to do it using Mealy model, you have here y, and you have here a1, a0, x. So I can get y as a function in a1, a0, x. Okay, as you see here. So you have a1, a0, x, and then I can get y this way. Or I can use Moore model. In this Moore model, because you can notice here, y, you can notice from this diagram, y only depends on the state. So if it is 0, 0, always has to be 0. If it is 0, 1, always has to be 1. Okay, so in this case, I'm going to make a new table, as you see here in this new table. So if you are in state 0, so always, if it's state 0, always y has to be 0. If you're in state 1, always has to be 1. If it's state 2, always you have to be 1. If it's state 3, always you have to be 0. And then from this one here, you can calculate y. So now y is going to be a function only in states. That's why this one is more designed. Okay? Again, what I'm saying here, you can design if you just take y here, if y here, design it using a1, a0, x, automatically this will be Mealy model. Why? Because x is already input here. Okay. The other way, if for some reason you want to work it using only Moore, in this case, you should make a new table here. It's actually not a new table. It's here you can see if it is 0, 0, always here it has to be 0. Always. If it is number 1, always it has to be 1. If it is number 2, always it has to be 1. If it is number 1, always it has to be 0. You got what I'm saying? So in suppose case, regardless what is x. So yes, I can make it this way as I explained. Okay, guys. Any question? So now I finished the sequence generator part. Now we are ready to do the first part of the project. Next time I will talk about detector, sequence detector. Okay. You need to say some. I will correct the last example.